So today I want to talk about Pauli strings and Pauli transfer matrices. This is what Lennart, Sabiata and I were working on in our last project and also working on right now. I want to give you a brief introduction into the basics and the definitions, and I also want to share with you the insights that we had. So it all started when Sabiata approached Lennart and asked him if there would be any possibility to do a faster Pauli decomposition. The topic of Pauli transfer matrices came up afterwards because we received a mail that asked us basically to look into that. I haven't heard the name Pauli transfer matrix before, but after I read the definition, I remembered that I saw something like this before, but without the name Pauli transfer matrix. So I got a quote from that paper where I saw it the first time, and I think it quite accurately describes as a representation of linear maps into the Pauli basis. So let's start with the topic of Pauli strings and the Pauli decomposition. So as the most basic definition, we have the Pauli matrices, and we include the identity to have a basis of the 2x2 complex matrices. To define the Pauli strings more easily, we also define those labels from 0 to 3 to enumerate the Pauli matrices. So as a first fact, we know that they form a basis of the 2x2 matrices. The complex 2x2 matrices. They also form an orthonormal basis with respect to the scalar product defined as scalar product of A and B is equal to the trace A star. Pauli matrices are mostly used to describe single qubit gates and also Hamiltonians, but they can also be used to describe quantum states, especially with this relation to the Bloch sphere, where the density matrices can be described as rho equals 1/2 the identity plus 1/2 times the vector times Pauli vector, where this is to be understood as being ni sigma I, the sum with ni. But using tensor products of Pauli matrices, one can also describe multi-qubit operators. For example, for n qubits, we define a Pauli string via a string of zeros, ones and twos and threes. So for example, 0, 1, 0, 2, 3 would correspond to identity tensor X, tensor identity, tensor Y, tensor Z. Or one can also describe it as X2, Y4, Z5 if one wants to indicate the position where the Pauli strings have non-zero entries, so non-identity Pauli matrices. Pauli strings are used a lot in simulations, and there are also a lot of specialized libraries such as Pauli array library. Also the Pauli strings form a basis for the n qubits, just as the Pauli matrices and the identity do for the single qubit. So now we are at the first goal of the talk, which is the Pauli decomposition. It is the task of calculating these Pauli weights, these omega t, and the usual approach is to calculate them as omega t is equal to scalar product of A and sigma t. So for 4 to the n Pauli strings, we have to compute the trace and the multiplication of 2 to the n times 2 to the n matrices. Since this is very inefficient, we came up with an approach that goes qubit by qubit. So for the first qubit, we write A is equal to sum over T in Q. So the four Pauli matrices in Pauli matrix tensor product with the accumulated matrix weight, which is this omega T star, which is a matrix in a smaller space with 2 to the n minus 1 times 2 to the n minus 1 entries. And so we calculated basically that the cumulative matrix weight is the trace of the first qubit of A sigma T tensor identity to the n minus 1. And doing this recursively results in a big speed up, which we used in our algorithm for tensorized Pauli decomposition. And this is basically a classical divide and conquer scheme where you have your sort of computational tree and you split out your computation into smaller computations that can be easier handled. So in each step we have 4 to the I branches where the computational cost or the matrix addition that we use in calculating this trace would be of order 4 to the n minus I, which is the size of the matrix basically. And so summing this would result in something of the order of O of n times 4 to the n, which is by now also the optimized scaling achieved by other methods. But this method has the advantage that if one of those cumulative matrix weights would be 0, then we basically would cut the branch and reduce the computational cost by a lot. So this scheme can not only be applied to the Pauli basis, but basically to any basis of a tensor product. So if you have basis for each tensor factor, you can also do general multilinear maps, so tensor products of functions or maps or matrices, apply them to each tensor factor separately or iteratively. An example that some should know would be the Q-hipster algorithm, where you apply unitaries or tensor products of unitaries to a chain of qubits. The computational scheme for a Fourier transform might look similar, but there we have also a swap of tensor factors and also not only one tensor product of functions, but a sum of tensor products of functions. And now to the second part, the Pauli transfer matrices. For the Pauli transfer matrices, we consider functions that map matrices to matrices. And the Pauli transfer matrix is then the representation of this map in the Pauli basis. So the Pauli transfer matrix of this function would be a 4 to the n times 4 to the n matrix. For the Pauli transfer matrix, we use the lexicographic ordering. So for example, in the 2-qubit case, we start with 1, 1, 1x, 1, y, 1, z, x, identity, and so on. One example for such a map would be a quantum channel, which is a completely positive trace-preserving linear map. Of course, the Pauli transfer matrix is not the only way to represent a quantum channel. One way to represent those quantum channels is the so-called Choi matrix, which is defined as the sum over I and j. I, j, tensor product, the channel of ket ij. For the Choi matrix, we can find from the representation easily the Pauli transfer matrix by seeing that the channel applied to the Pauli string is equal to the cumulative matrix weight with regards to that Pauli string. Then the Pauli decomposition of this cumulative matrix weight would be the column of the Pauli transfer matrix. Another representation that is often used is the Krauss representation. The Krauss representation says that channel applied to rho is the sum over I of ki dagger rho ki. Of course there are also other representations, but it might be a little too much to state them all here. So in particular for the Krauss representation and for unitary channels we have to look at this conjugation. So we use that, we can again write U as the sum over the Paulis, sigma T tensor the cumulative matrix weight. So in each step we can use that sigma T tensor omega T star P tensor P star sigma T tensor omega T star dagger is sigma T P sigma T dagger times omega T star P star omega T star dagger. And this again defines the recursion where we calculate the Pauli transfer matrix of the individual qubit and of the remainder, and then do the tensor product of the Pauli transfer matrices. For people that do simulation, also using the Pauli transfer matrix in the time evolution might be beneficial. So if we only look at the Schrödinger equation, then we might just want to use the commutator, but maybe we want to do something that is not unitary, where we have a kind of Lindblad master equation evolution. So again, both cases can be done recursively, but this time in the recursion there are actually two terms instead of just one. So if we take the commutator of the tensor product, then we get 1/2 times the commutator tensor the anticommutator plus the anticommutator tensor the commutator. And a similar recursion relation holds for the anticommutator. But here we have 2 times the commutator and 2 times the anticommutator. So here again we can use the cumulative matrix weights to do this kind of recursion, but this time we have the tensor product of the Pauli transfer matrix and an additional addition. So in the end, my takeaway from this project so far is that there's a very high competition in trying to optimize the Pauli decomposition, and I think that also helped to kind of get a motivation in there. For the Pauli transfer matrices, I think there are a lot of possible optimizations and I think there are not so much sophisticated schemes around yet, so that this might be a cool thing to explore, and also to find new formula like we already found. So what was a good motivation is that those kind of algorithms are very helpful for simulations, and so the need to improve or to make them faster. But in the end, I think it's just a classical algorithm which might help for quantum computing. Yeah, thanks a lot for listening, and see you maybe in a while.